Now we're going to talk about series connection. Okay, so there are three capacitors, as you can see on the figure on the right side. They are connected in series, and it's because the same charge will be on them. Okay, and so this is the key thing. The charge on each capacitor has to be the same. Then you understand that they are connected in series. But the potential, it is not going to be the same, but what you see is each potential. So you have that battery potential V here, and this one has V1, V2, and V3. They are not necessarily the same. They can be if C's are the same, but they're not necessarily going to be the same. So we're looking at the general case. The V, the battery potential, is going to be equal to the sum of those three. Okay, and again, previously we added up the charges. Now we are adding up the potential. So whichever, like the one is constant and the other one is simply add up. Okay, in the series, the charge is the same, potential adds up. In the parallel, potential is the same, charge adds up. Okay, so starting from here, we will find out the equivalent capacitance as well. So what we have, once again, we are using the electrical equation. So when you have a circuit, this is the equation to use. Q is equal to CV, and if I pull this V from here, it will be, I need to divide both sides by C, right? So this is how V is defined, the voltage. So I'm gonna write that, and I know that Q's are the same because, again, the charge is the same on series connection. And they have, again, they may have different capacitors, so we're going to write it in general. So V1 is going to be Q over C1, V2 is going to be Q over C2, and V3 is going to be Q over C3, okay? And when you look at this, this becomes Q 1 over C1, and factoring Q out, 1 over C2, and oops, didn't mean to close the parentheses yet, plus 1 over C3, okay? And this is V, right? V is equal to Q times that. And remember how you use that general equation. I'm gonna write it here again. Q is equal to CV. If you write it in this form, you have V is equal to 1 over CQ. Don't know why I'm making G's for Q's. So you're putting the C on the other side, and that's what you're getting, right? So if you look at that, if you compare these two equations, this should be equal to 1 over equivalent capacitance, right? And it's going to be 1 over C1 plus 1 over C2 plus 1 over C3. That's the equation. Just make sure that since this is 1 over equivalent, it's not the equivalent capacitance, so you have to flip everything after you get the right side, and that's usually where people make a mistake. So why the charge is the same? The charge is the same because, again, they're just, the charge is flowing through the, like, think about the wires as like the pipes, okay? And first of all, before I talk about the charge, I want to talk about the potential. And like between the elements, like any different color means they're different potential. Okay, I'm gonna just use a bunch of different colors here. So because like where I put those colors, we don't have any batteries or capacitors, right? Like they are in between those colors. So you keep having a potential difference. Okay, so you can see that C1 is, the voltage of C1 is between yellow and green. It's not the same thing as green and blue or blue and purple. That's why they don't necessarily have the same voltage across them, and we don't assume they have the same. But the current is the same. It's because like current is like the charge, sorry, I didn't mean to say current. The charge is the same because this is like the charge flow is like a water flow through the pipe, and pipe being the wires. So you can see that there's only a single loop, right? And charge will be conserved just like water will be conserved. If you like send 1 kilogram of water, it's going to come back to 1 kilogram of water, right? It's the same thing. You send the charge Q, you will get the Q back because it's conserved, okay? You cannot just have it disappear for no reason. So just because of that, the same amount of charge will flow through them. Okay, so that's why they're connected in series. And this can be drawn as, again, once you have your capacitor, equivalent capacitor, you can replace all those three with one of them and simplify your circuit diagram and show that. Now the equivalent capacitance does actually have the same potential with the battery, but none of those C1, C2, C3 have the same potential as the battery potential. And the total charge is the same as all of those in the series connection, and it's also the one on the equivalent capacitance. So one thing that you may think, and I'm just going to write what we said here, Q is equal to equivalent capacitance times potential difference, and we got that 1 over C equivalent was equal to 1 over C1 plus 1 over C2 plus 1 over C3. So to get the equivalent capacitance, you need to take the inverses on each side. Okay, that's going to be equal to C equivalent. Because of this algebra, what you really see is C equivalent will always be less than the individual C's. So you should always check your algebra. Let's say the lowest one was like 1 nanofarad. Then you should expect that C equivalent will be less than that. Okay, so once you know that, it is nice to check if your algebra makes sense, because if you forget to take the inverse, you're gonna get a bigger value, and that's kind of good to know. And so knowing this, and kind of think about the lab we did on Thursday, what do you think when you roll up that aluminum folio and like the wax paper in between, right? We rolled it up, and we also flattened it. What do you think was happening there in terms of, like, it wasn't one capacitor anymore, it was multiple capacitors connected, but what was the connection? Was it parallel or in series? I want you to give it a thought about that, because remember that you were able to increase the value with the after you roll it and flatten it. So that should tell you whether the connection is parallel or in series. Okay, we'll talk about that in the class. So to summarize it, capacitors in parallel have the equivalent capacitance of, and if you don't necessarily have only 3 of them, in more general, we are going to sum up CI. So it's going to be like basically 1, 2, and however many you have, you're going to keep adding them. And for the capacitors in series, we have the equivalent capacitance, as again we are adding it up. I'm just going to write it this way, CI, but the inverse after that. So you're adding all of them up, and that is basically 1 over C1 plus 1 over C2 plus however many you have, but don't forget to take the inverse of that.